Rack and stack, installing network routers. By the time we're done here, you will be able to understand the basics of IP addressing and be able to configure and install a network router. Everything that we've done so far has brought us up to this point, installing the router. The router will segment our network from the rest of the world and safely bring in internet access. Well, let's first explain what a network router is all about. And don't just read through the bullets because you'll be very confused if you do. I need to unpack them. A network router contains networks. And it's often represented in a network diagram with a symbol that looks like this. Now, in our environment, we have connected a switch into our system, actually a couple switches. And those switches connect to devices that are plugged into the networks, even a wireless access point, which allows wireless devices to attach in there as well. And the more devices we add, the more chatter is introduced in the network. Imagine you and a group of friends went to a park to play basketball on the weekend, and there was 3 of you, and you played and had fun, and you did it the next weekend, and before long, some people started watching, and they're like, hey, can I join? And you're like, yeah, sure, come in. And before long, your 3 friends turned to 10 to 20, and now not everybody can fit, and people are having to sit on the bench and wait their turn, and so on. That's kind of what happens with this network chatter. The more and more your network grows, the busier it gets, and so you have to reach a point where you segment it. And by segmenting, technically speaking, the router says all the broadcast traffic, that's what I was calling chatter, will stay behind this line. Everything else can move past it. And that's what I mean when I say moves data between networks. And these two statements seem like they're opposite. It contains networks and yet moves data between networks. That's because broadcast traffic is great for finding people within the network, but it gets downright unruly the larger your network environment grows. So we have to contain it to prevent other networks from hearing all those broadcasts and having to process all of that traffic. But a router allows data to move between networks in a unicast kind of way. See, when your computer says, I want to go to google.com, it's asking to go to a very specific server, meaning from my computer, one device, to one server. That's what unicast messages are all about. And when the router receives that unicast message, it says, oh, okay, this isn't just normal chatter. This is going to a specific destination. I'll look at my routing table, we'll talk about that in just a second, and forward it through. A router also connects dissimilar networks, the most common one being your private network off to the internet. But we could also define dissimilar as the accounting department, and anytime I draw a line like that, that kind of represents a switch, the accounting department right here, and the public Wi-Fi network where anybody can attach. When I start using examples like that, you should get the idea in your mind of security. Truth be told, routers and firewalls are very similar, as in the lines are almost completely blurred between the devices. Technically, a router does exactly the things that I've described, whereas a firewall introduces security systems, saying, well, the public network can't reach the accounting group and the internet traffic can't get to these guys if it wasn't requested to come in, and so on and so forth. But over the years, things that are claimed to be just routers also have a lot of those same functions, so the line continues to blur between them. Now, because these are software-based, they're never as fast as a switch. A switch can move data in and out of its ports at wire speed, as fast as that wire is able to transmit. Whereas when it comes to the router, there's going to be some processing time where it actually looks at the packet, figures out where it's going, sends it on its way. Now I'm talking in terms of millisecond timeframes, very fast in terms of human standards. However, there is some significance there when you compare it to a switch that has 0 delay. Now, to understand a network router, you have to understand the basics of IP addressing. So I'm going to transition us from the switching world by first off explaining that most of the time in network diagrams, switches are represented by this icon right here. And oftentimes it doesn't matter how many switches there are. High-level network architects will just say, well, the 2, 3, 5, 6, 9 switches in that wiring closet pretty much represent a switch, because all they do is connect all the devices to the network. It doesn't really matter if there's 1 or 9 switches there, it all serves the same function. Stuff plugs in. Now, I mentioned earlier in the series that devices have MAC addresses burned into their network card. And that's great, and it works for communication within a switched environment, because that's what switches do, is memorize those MAC addresses so it remembers where the devices are at. But when it comes to normal network communication, these devices use IP addressing because it lets them know where they are in the world. See, MAC addresses have no rhyme or reason. You just get what you get when you buy the network card. It's burned into it. IP addressing is configured by a network administrator. And you'll never see an IP address without a subnet mask, because they're both required to make a device functional in a modern network environment. At a basic level, if you take a subnet mask and line it up to the IP address, you'll be able to tell which portion of the IP address represents the network the device is on and which portion represents the actual computer in that network. The 255s represent the network. The 0 represents the computer on the network. A lot of people will call that the host. So looking at this network right here with that subnet mask, I can safely say this represents the 192.168.1 network. I know that everything on there will start with those numbers. If I were to plug in a computer and assign it 192.168.2.50, it just simply wouldn't work. It wouldn't be able to communicate with these guys because it would think it's on a different network. And this is the logic of how all network communication works. When this computer realizes that some application or something that you are doing on the computer is trying to access the network, it's going to look at the destination you're trying to go to. Let's just say we typed in a ping command, which is a command that tests network connectivity. And we said, I want to ping 192.168.1.11. The computer would look at its IP address and say, okay, well, I'm 192.168.1.10. Look at the subnet mask and go, oh, okay, well, I'm the 192.168.1 network. And then it would look where you're trying to go. You're trying to go to 192.168.1.11. Hey, that guy's on my network. So I should be able to reach that guy by sending a broadcast. And it does. Technically, that broadcast is called an ARP message. That stands for the Address Resolution Protocol. This computer, that has so many arrows pointing to him at this point, is trying to figure out what is the MAC address of that computer. Because it knows from a switch perspective, in order to communicate, it has to send it with the destination MAC address of that computer. And so that ARP broadcast message goes out. It goes to every computer, but only the computer with the IP address. Good grief, I've got to clear this off. Only the computer with the IP address that was being requested replies and says, oh, that's me. So now this guy communicates directly with that guy through the switch. Now let me expand that initial small network a little bit more and introduce a router and an internet connection, because in today's modern world, most of our communication doesn't go between devices on the same network. It goes from the device out to the internet. When you open a web browser on your computer and go to a website, I'll just say google.com, the computer will translate that name into whatever IP address Google has. If you like to see it in action, just open a command prompt on your computer and type in ping google.com or ping whatever website you want to know what IP address they have, and you'll see it right there. 172.217.4.174 is one of the many IP addresses, I'm sure, that's associated with google.com. So the web browser on that computer is like, hey, that's where I want to go. 172.217.4.174. And the computer immediately knows, because it's looking at its network. He goes, well, that's not on my network. So I can't just send an ARP message to reach it, because the job of the router is to stop broadcast. Imagine how crazy our world would be if there were no routers and everybody was just connected together. There'd be bajillions of broadcasts every single second, and the whole thing would break down because our networks wouldn't be able to keep up with that, nor would all the devices receiving all of those broadcasts. They would all freeze. So when the computer realizes, hey, that IP address is not on my network, he then says, I'm going to send it to my router. Technically speaking, you'll see that in IP address configurations as the default gateway. So technically, there's three pieces that make our computers work in our modern worlds: the IP address, the subnet mask, so it knows what network it's on, and the default gateway, so it knows how to get off of its network. One more key piece that most devices have is a DNS setting, and that's the server that translates all of those names to IP addresses. So now let's start gluing all of these puzzle pieces together. The IP addressing that we set up for our internal network will almost always be a private IP address. And you can see the three ranges of private IP addresses listed right there. Those are IP addresses that you can set up without registering with the government. It's kind of like, remember we talked about wireless frequencies in the wireless access point video? And I said there's some frequencies that are unlicensed, so you can just set up a wireless access point wherever you want in the 2.4 gigahertz or the 5 gigahertz space. This is kind of like unlicensed IP addresses. You can use them whenever and wherever you want because everybody duplicates them all over the world. Now on the internet, we use something known as public IP addresses, which in a nutshell is pretty much everything outside of those ranges. The IP addresses can be assigned to our devices either statically or dynamically. That actually stands for the Dynamic Host Configuration Protocol. That's what most people use because it's very tedious to go to each computer and type in what IP address it is and what IP address is. When the computers start turning from tens to hundreds and they start going mobile and that device went bad and you have to bring a new one to replace it, it just becomes unruly to manage this. So we'll set up often what's known as a DHCP server and give it a pool of IP addresses. There's my little pool to hand out to these clients when they come online and request one. That functionality is often integrated into the router as well. So you could set this up as a DHCP server to hand out IP addresses to computers on the inside. And there is one final ingredient that makes the whole thing work, and that is NAT, Network Address Translation. See, if people are duplicating these addresses all around the world, the system would blow up if there was no way of hiding them. So for example, here's you and I sitting behind here in our network environment, and then somewhere out there is Intel, right? And Intel has duplicated those same addresses. Well, when we're communicating out to the internet, how does it know when it's coming from you versus a device using the same IP address at Intel? It's all hidden. Network address translation translates the private IP addresses right here behind the network into the public world out here. And the beauty is it uses a system of overload. That allows potentially thousands of devices using private IP addresses to share one public internet address. That is what has sustained the internet because technically we've run out of IP addresses. So NAT allows the billions of IP-enabled devices in the world today to share them. So now we'll be bringing a network router into our Office suite. We have a new DSL connection that's coming in, and we'll put the network router right there in the rack. This will bring in internet access to the entire organization. The router that I'll be installing is a Ubiquiti Edge Router Pro. Now, just for the record, I have no affiliation with Ubiquiti at all. The reason I like their stuff is they strike a great balance between ease of use, meaning they have a great graphic interface that you can use to configure them, and powerful capabilities, meaning they have a command line interface behind the scenes that allows you to do a lot more than most consumer-grade equipment would. Couple that with a really great price point on all of their routers and wireless access points, and they make the perfect lab equipment. Now, each one of these interfaces on this router can connect to a different network, and we are in no way going to use all of them. Ethernet 0 will have connected to our stack of switches. Well, technically 2 switches that we have installed, and that will bring all the inside traffic out to this interface, which will connect to our DSL connection. We'll use private IP addressing for our network right here. We'll actually set this guy up as a DHCP server, and we'll implement NAT as the IP addresses move from the private world into the public internet. These other interfaces we could use as the network grows, if we wanted to create different segments of traffic, or maybe install a redundant internet connection should this DSL provider go down. Notice over here on the right-hand side, those are SFPs, or at least the slots for them. That's small form pluggable modules that go inside of there, typically used for fiber optic connections. I'll mention this now because I'll likely forget if I don't. Ubiquiti also makes an Edge Router Lite, which works perfect for a home environment. It has all the capabilities of the Edge Router Pro, it just isn't as fast and has fewer interfaces. All right, I got our Edge Router Pro right here. I'm gonna rack mount it right here. Now at this point in the game, you've seen this enough that you know how to rack mount things, but what I wanna point out while we're here is we have 2 feeds coming in. This is an internet connection from another office that we're gonna stop sharing now because we need an internet connection for this office. That's gonna come in on this port. So this port, this RT1 port right here, will represent the new DSL internet connection coming in. We'll need to route that down to Ethernet 1 interface on this Edge Router Pro once we get it mounted. All right, the router is in place. Now we're gonna use a blue cable so it stands out from all the rest of the black cables to route the incoming DSL internet connection down around into Ethernet 1. I'll route the inside interface of this router, the one that connects to the private side of the network, up and around to the top port of the switch that's gigabit 27. There you go. I'm using a white cable for that. I'm smiling because I'm sure there's a cable management purist out there who is looking at this going, you should have another cable manager between that firewall and the switch. And I would say, yes, if you are a cable management purist, you absolutely should. There we go. Now that we've got the router rack mounted and the ETH0 is connected to our main network, I came back to my desk and pulled up the quick configuration guide, just Googled it, and if I scroll down to page 10, this is what I see. Accessing the EdgeOS configuration interface, it says, okay, connect a cable to ETH0 that's connected to either directly to a computer or to your internal network. Then configure the Ethernet adapter on your host system with a static IP address from 192.168.1 subnet. That's the network that we were just talking about, 255.255.255.0, right? And then it says, once you do that, launch your web browser and access this URL, 192.168.1.1. So this router is pre-configured from the factory to respond on ETH0 to that IP address. So let's do it. I'm going to open up the control panel, and let's go to the network status, change the adapter settings, and my LAN adapter. That's the one that's plugged into the network switch. Now, I actually have a static IP address on it right now, 10.225.1.6. That's my network that we're borrowing from somebody right now that we're going to change over completely. So for now, so I don't lose my internet access and lose all of my recordings that I'm talking to you on right now, I'm going to add this as a secondary IP address, 192.168.1. And you can pick anything all the way up to 255 is the last possible, but 255 you can't actually pick. So 254 would be the last valid. So I'm just going to pick 55. It automatically fills in the subnet mask because that's actually one of the most common networks in the world. I'll click on OK, and we're good. I'm going to open a command prompt, and I'm going to try pinging that. Ping 192.168.1.1. That's how you can see if it's online. It is. Good. Let me now open a web browser. Bring that into the page. And we'll do what the guide said, HTTPS 192.168.1.1. Let's see what we get. It's just going to say this is not secure because it's a untrusted certificate. That's okay. You don't want to have to buy certificates for your private equipment. Cool. We're there. So it says EdgeMax, Ubiquiti license. Sure. Hang on. I didn't look at that in the quick guide. There we go. UBNT will be the username and password. UBNT, login. There we go. We're now at the configuration wizard of this Edge router. I'm not much of a wizard guy, so I'm going to go straight to the dashboard. It says, warning, you cannot come back. Yes, that's fine. I'm out of here. The first thing I'm going to do is look at the interfaces that I have right here. So there is my local interface. That's ETH0, 192.168.1.1 is its IP address. ETH1 is supposed to be my internet interface, but you can see right here, it's disconnected. It doesn't have anything plugged into it yet because I haven't plugged in the DSL modem. Let me do that now. And there we go. We've got it now connected, plugged into the DSL provider, and they gave us a static IP address of, so we'll use manually define the IP address, 10. Man, it looks like we got a little, well, this is an old version of the software. I'll have to upgrade the firmware on this guy eventually. It's actually, 200.1.1.53/24. Now, /24 is the same thing as putting 255.255.255.0. So I'm going to click on save. And we now have an internet address. So there it is. We're connected to the internet. Now we need to set up the routing and the NAT. Okay, I can't help it. Before I do that, I've got to upgrade that firmware. This is 1.3, and they're currently at 1.91, so I'm going to download that new version of the firmware and get this thing upgraded before I continue on with the configuration. We're talking years and years of differences and upgrades in the firmware, so I'm going to click the system menu right here, scroll down to upgrade the system image. We'll hit upload the file. There's the image I just downloaded. Double click that. We'll let that thing copy over and reboot the router to get on the new version. Copy done and reboot. Yes. All right, we are rebooted. Let's get logged in. UBNT is the default password. There we go. Now we're on 1.91, and I can see I even have more tabs going across this top from features that have been added over the years. Okay, two major things that we need to do to get this thing fully functional. One, we need to add a default route, and that is essentially telling this router, you know what? Anything that you don't know about, I want you to send it there. Now remember, we've got a router here that's connected to the internal network, our switch network, and our computers are sitting inside waiting for that internet access. We've got a DSL connection plugged in to the internet. This guy has the IP address 200.1.1.53. That's the ETH1 interface. This guy has the IP address 192.168.1.1. That's the ETH0 interface. A router is able to tell you how to get to different IP addresses. That's what it does. And in this case, this router is not going to be very intelligent because we're simply going to put a default route in here saying, you know what, anything that you don't know about that's known as an all-zero route, send it off to the internet service provider, who actually has a router sitting right here at 200.1.1.1. The second function this router is going to do is NAT, where it's going to translate all of these private addresses into the public addresses out on the internet. So I'm going to go up here and hit add a static route. Destination network will be all 0 /0 as the subnet mask, essentially saying everything goes out there to 200.1.1.1. That's the next hop IP address of where it's going. And I'll call this the internet route. And we'll make it the distance of 1. Now, I know I'm dumping a lot of stuff right here, like, what is all this stuff? This is simply saying this is a really good route. That's what the distance of 1 means compared to a not so good route that maybe would be a distance of 200 or 220 or something like that. It's a believability of the route. I see that it's enabled, showing everything's going out there. I'm hitting save, and now this thing should be able to get to the internet. I can see that static route has been added, but I'm not done yet. I still have to go in and configure NAT. You can see NAT is enabled. Let's see what that one rule says. Now look at this. Ubiquiti has done something kind for us. They've said, I've got one rule in place. Oh, I'm dragging and dropping things around. One rule in place. Description is blank. Source is blank. Destination is blank. And then it says translation masquerade to Ethernet 1. Now, what does that mean? And notice we're seeing this count already starting to tick up. Well, what that is a NAT everything rule. Again, we've got that network of private addresses sitting over here. How many private addresses? I don't know. A lot, maybe. It depends on how many computers we have attached. And by keeping everything blank right here on all of the information of what we are going to NAT, but defining the translation, saying masquerade, what does that mean? Hide everything behind the IP address on Ethernet 1. As long as things are routing through this router, that will automatically do NAT out to the internet. Now, he said that's our last thing, but I want to check one more thing, and that's DHCP. And I can see right here it says DHCP is enabled. Remember, this is the piece that hands out the IP addresses to the network. And I can see right there, LAN 1 is already pre-configured for the subnet. This is thanks to Ubiquiti automation, I suppose, with a pool size of 220, meaning it's got 220 addresses that it's able to hand out. Now, at this point, none have been leased. So let's boot a computer on that network and see if it gets an IP address. So I'm bringing my Windows 7 not genuine machine into the picture because it's a lab machine. So I'm going to open a command prompt, start menu, CMD, and type in ipconfig. Sweet. I see we've got the IP address 192.168.1.21 sitting right there. That's got to come from this default gateway. I'm going to do a quick ping to 4.2.2.2. That's a internet DNS server. That's awesome. Looking good. We actually have one machine. So I'm going to come back to my router right here, and I'm actually seeing 4 leases already. Let's click on the actions and hit view leases. There's my .121 address going to Win7 Jabber IPC. That's my computer in-house right here. And then it looks like a couple other have also obtained an IP address. So we are looking really good on this router. Oh man, I could feel myself just getting faster and faster and cramming more and more and more as we get to the end of that router setup. Once you open the can of routing, there's no turning back. There's so much knowledge that just can explode out of there. Well, I said at the beginning, you will understand the basics of IP addressing, be able to configure and install a network router. So now it's your turn. Research the Soho routers from 3 different vendors. Just pick some. Cisco, Netgear, D-Link, Ubiquiti, some of the ones that you'll commonly see out there. I'd also throw SonicWall into that mix. You'll see more firewall functionality coming out of them. List at least 3 key features provided by each type of router that you see. Then create an IP addressing plan for your home or office. Then it's time to do it. Purchase a network router. I would really recommend one of those Ubiquiti Edge Router Lights. I looked at the reviews on them just a moment ago, and I saw one of the people that said, "You've got to be a network engineer to figure this thing out." And I'm like, excellent. It's such a good, cheap device that strikes a balance between that ease of use / moving into network engineering mindsets. Configure the IP addressing appropriately on the devices inside the system, whether you want to use static addresses or DHCP, then configure the public IP address and NAT on the router. From there, test your internet access and see if it's working.